Okay, I think we're live. Yes, we are. All right. Okay, cool. So before we get back to hash tables, I'd like to discuss the homework, which seems to be causing a great deal of consternation. Maybe consternation is a good way of saying it. So let's talk about ternary trees. Okay? Alright, so what is a ternary tree? The answer is you're supposed to, basically the idea is, and I didn't want to exactly say, right, but I think that maybe the hints are not good enough, or I don't know, something like that. So, you know, the problem doesn't exactly tell you. But then you should ask yourself, what is a binary search tree, right? A binary search tree is, you know, it's a structure where basically you have a node, and that node can have two children, right? And it has a single value, right? So it has a value. Let's even do it as maybe a dividing line. Well, I wish it wouldn't. There. Nope. There. Okay, so, right, all things that are less go to the left, and all things that are greater go to the right. So that part we know. Yeah. Okay, so that's what happens, and you have a single value, right? Your value is going to be v, right? So if it's less than v, it goes to the left, and if it's greater than or technically or equal to v, then it goes to the right. Okay, so that's the definition of a binary search tree, right? It's some structure where now these nodes can also have, you know, nodes that are popping off of them based on the same rule, right? But that's the whole idea of a binary search tree, is that there's some structure like this where less goes to the left and greater than or equal to goes to the right. Okay, so what is a ternary tree? The answer is, well, that's a little bit more complicated. But in this case, a ternary tree, and if you notice, you're going to have P left, P center, and P right. So we're going to have one more node here, like this. And so what I'm going to do is I'll draw something like this, right? And so now you're going to have two values. I'll call it V, and the other one I'll call maybe W, okay? So these are the two values in a single node. And let's see, hang on. There we go. Okay. As you notice, every node needs two values now. So nodes need two values. Let's shrink the font size. Let's change it to, say, 10. So nodes need two values, right? And given them, I mean, so they can actually have one value. So they can exist with just one value. But generally, you know, generally that's difficult, or I wouldn't say it's difficult. That's a kind of edge case. Okay, and so basically think about it this way, right? If you have two values, what do you really have, right? Think about the number of ways that things can happen, right? If you're given any x, right, x can either be less than v, which is less than w, let's assume, or v can be less than x, which is less than w, or v can be less than w, can be less than x, right? So those are the three options, right? Either x is less than both of them, x is in between, or x is bigger than both of them, right? And so, there are three options here. Interesting. Now, of course, you might ask, what do I do with an equal sign? Equal cases. The answer is same thing as with a binary search tree. You just pick either left, right, or you pick a direction not at random. I shouldn't say at random, but you pick a direction, right? So that's the point here, is that there we go. Well, maybe I should make this one a bit bigger. There we go. Okay. Yep, so this is the idea of the problem, and I hope that this is enough of a hint to basically get you to the answer. I mean, yeah. Right, so what's a BST, and then what's a, I guess you could call this like a TST, right? A ternary search tree. And so I just basically want you to think through how you would make a structure like this, right? And so, and then the other confusion that I've seen a number of people, some people have asked me about, is what do I mean about this, like with no balancing operations? And basically, the whole reason I even wrote that, I mean, really I should have just deleted that sentence, that prepositional clause, I guess. Ignore it entirely. Or understand that it just means you don't have to balance the tree, do any rotations. You don't have to make up any kind of like an AVL TST, right? That's not what I'm saying don't make an AVL TST, right? That's what I'm saying. That's all and that's literally all I'm saying with that, is that I'm just trying to specify that you don't want to do extra work, and that's it. So it's not a limitation, right? It's actually just a yep. Okay, and then basically I think part B is just it's a standard induction proof. And then part C is you use your algorithm here, whatever algorithm you come up with, to insert the nodes into the tree, right? And you should draw a diagram, okay? So that's the point about constructing a tree by inserting a certain set of things. So anyway, this is the idea. Okay. And then So for the heaps, and then someone asked a question about the heap structure in problem number 1. And so I just want to, maybe I'll say a word about that. So for instance, let me just do an example, I guess, right? Let's just do an example. Let's draw out, right, some kind of tree structure. And, okay, let's draw that out. I don't know, I was trying to align them so well. Doesn't matter. I can just do this, that. Okay, and then maybe I'll even put in like 2 more nodes, maybe here and here. Okay, so let me do an example for you, okay? Because maybe I actually did this example the first semester I gave this homework. Just trying to think. Because this is a recycled homework, so. Because I actually do like these problems. Okay. So remember that it doesn't matter if this is a heap or a binary search tree or whatever. What we're going to do is we're going to number the nodes, right? This node will be numbered, let's say. This node will be numbered 0. This node will be numbered 1, 2, 3, whoops, 3, 4, 5, 6. At least I think. Is that how we want to do the numbering? Oh, no, I'm sorry. Nope, we don't want to start numbering at 0. We actually want to do the anti-computer science thing and start numbering at 1, which is why I was telling you to do the binary expansion of m plus 1. So you'll see what I mean in just a second. So let's assume that this is a tree, and what we're going to be doing is we'll always be inserting to make the tree a complete tree. So like in this case, we'll insert left, right, left, and then the next time we'll insert left, right, right, and then the next time we'll insert right, left, left, and then we'll insert right, left, right, and right, right, left, and right, right, right. So what are the binary equivalencies? What are the expansions of let's see, if that's the case for equal cases, will the ternary be tree in proper order to still achieve a perfect ternary tree? I don't know. Second question, which sorry I didn't see it immediately. Let me make sure that the questions are... So the answer to the second question in terms of, I'm telling you to insert one number at a time, so you only fill V, and then on the next one you might fill W. Yes, exactly, that's right. Is there a specific order that you'll follow? Is there an equal instance and it can go to a random side? No, I say it's not random, right? I was going to say it's random, but random is the wrong thing, right? It's just like for a binary search tree, right? It doesn't matter if you insert all the equal nodes to the left or if you insert all the equal nodes to the right. The only thing that matters is that you make a decision and you stick with it, right? It depends on where you put that equal sign in your implementation. Now, in terms of being a data structure, in terms of all the theoretical stuff, none of that actually matters, right? The only thing that matters when you make that decision is literally just where you put that equal sign, and then it'll determine where all the equal things go. And the reason why you have to be consistent and the reason why it cannot be random is because if it were random, then the problem is when you get to a certain node, you don't know which direction it went, right? So if I say, like, if I'm making a binary search tree, let's say that this node is equal to, say, 5, and then this node is equal to 3, and this node is equal to 7, and then I insert another 5 node, and what happens is I say, okay, I'm going to randomly choose right versus left, right? So I'll choose left this time, so I'll put it over here. And then, I say, okay, now search for the number 5, and the answer is you find it here. But what if I say search for all the number 5s, and you say, okay, I get to here, and then the problem is that I don't know whether the number 5 should occur this way or whether or not they should occur this way. Because if I made any random selection, right, if I just use like random mod 2 or something like that, then there would be a problem here because I wouldn't know whether it was here or whether it was here. Like basically, if you put the node here, you wouldn't necessarily know if it's this connection or this connection that's doing it, right? And that's, you don't want that in a binary search tree structure, because if you have that, then you have ambiguity as to which direction you would be searching, right? And it's the same thing for a trinary search tree. If things are equal to V, maybe you stick them all to the left, or maybe you stick them all to the right of V. Or if it's less than or equal, if it's equal to W, then maybe you stick it all to the left of W or the right of W. But you have to make those decisions. As I say, what do you do in the equal cases? You pick a direction, and it's as simple as that. You pick a direction. So, each number in part C is 2 digits. Definitely not. No. To the question after that. Each number in C is 2 digits. Absolutely 100%. In no way is that the case. No. Okay. No. Okay, good. Okay, so now let's get to what is a binary expansion. Basically, a binary expansion is just whatever that number is in binary, right? So 2 in binary is 1, 0. Right? And then 3 in binary is 1, 1. 4 in binary is 1, 0, 0. And I'm basically giving away the problem here, which is why... The only reason why these problems are a little bit vague is that if I say any more, then the problem becomes trivial, which I'm currently doing, which is, I guess, okay. It's not a... it doesn't matter, really. 1, 1, 0. 1, 1, right? 8 is equal to 1, 0, 0, 0. Guess I have to do something here. Crap, come on, let me modify. There we go, okay. 1, 0, 0, 1. Okay, so at this point what I'm going to ask you, and again, I think, unfortunately this is just kind of giving everything away, but whatever. So, here's the question now. Can you describe a path down one of these heaps, trees, whatever, using ones and zeros, right? And the answer is, well, it looks like to me there's always a 1 in front, right? There's a 1 here when this just means the root. But then there's a 1, 0 here, which means, okay, we went left. A 1, 1, which means we went right. 1, 0, 0, which means we did 2 lefts. 1, 0, 1, which means we did a left and then a right. 1, 1, right. 1, 1, 0, so that's a right and then a left. You ignore the leading 1. The leading 1 is kind of irrelevant. You just look at the 1, 0 part, right? And then here you get a 1, 1, which just says 1, right, right. This is all zeros because you ignore the leading 1, so 0, 0, 0 is just left, left, left. And then here it's left, left, right, so 1, 0, 0, 1. And that's basically, I guess this is, it's hardly a hint, right? I'm basically spelling everything out at this point, so it's okay. Yep, so that's it. I don't want to say too much more because I think I've given away too much already. Okay. Basically, the point is there, the only reason why I wanted to go through that is just to understand that, when you're doing the array-based heap stuff, the fact that you actually can just calculate wherever you currently are in the array-based heap and insert at the end is actually doing a very interesting and kind of complicated operation, which is determining its position based on, its binary expansion and sticking it in the right place, right? Because if the next thing you stuck in was 10, right? If you put in a 10 as the next node, and of course let me put it here so that we have room to talk about it, and then we say, okay, it's going to be to the left, then the question is, what is the binary expansion here? So the answer is, all I know is that it's going to be left, right, left. So it should be left, right, left, and then I just stick a 1 in front. And so as it turns out, 1, 0, 1, 0 is 10, right? Or I should say 10D is equal to 1, 0, 1, 0, B. Okay, so I think that's all I think I've answered all the questions that people have in the comments, at least about the homework. Let's see. And so basically, wait, draw? How many nodes will be in a perfect tree of height h? Keep in mind that a perfect tree, blah, blah, blah. It doesn't say anything about drawing. Right? Does it say to draw exclusively? Oh, in case I want drawings of well, oh, no. It doesn't, no, it doesn't say that. No, it says exactly the opposite of that, right? I want drawings of examples, break down cases, and then examine each case through a picture, right? Only revert to equations once the picture makes sense. So you gotta do equations. You need equations. But the thing is, I don't want just equations, because the whole point is that this is a data structure and it has a picture. No, it's okay. I'm I'm just saying, like, and I understand here where it says only revert, so maybe you think that you shouldn't use equations or something. No, I definitely want you to use equations. What I want you to do is use pictures before you use the equations, because at least sometimes what I would see on exams and stuff like that, I think before I gave this assignment, is sometimes I just see people like write out the inductive proof and they don't do any pictures and they don't show that they actually understand what it looks like. They were just like reproducing the lecture's proof but not understanding it. And that's why I want you to draw pictures, because in computer science, I hate to say it, it's like all these equations and stuff can sometimes get in the middle of understanding. So I definitely want a proof that uses equations, but the equation is like the last thing you write out, and you just write it out for the sake of like, here's what the picture does, and then here's what my equations say about that picture, and then here's the end of it. Because I think that it's necessary to have both pieces of understanding, right? If you can just write out the equations, it doesn't indicate to me that you actually have any understanding of like what's actually happening and why the thing is true. Like so the thing is that this is just going to be a straight up induction proof, and you can write up the induction proof without ever mentioning a ternary tree. You can do the induction proof on the algebra without ever actually having to deal with the data structure. You can just deal with the algebra. And that's what I don't want. I want people to actually deal with the data structure and then translate it into the algorithm, or whatever, data structure, algebra. Okay, so that's the point. Okay. So, all right, cool. I think that's it for the homework. Isn't that exciting? I like number 2. So don't overthink number 2, okay? The only thing I'm going to say about it is don't overthink it, right? Just literally do a rotate. What I want you to do is draw out a heap, rotate left or right on a node, and tell me what happens, right? And now you might say, but wait, it's not a heap anymore, or but wait, blah, 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 or but wait. Don't care. Just don't overthink it. Just draw out a heap, rotate a node, and tell me what happens, okay? That's what I want for number 2. And for number 3, it basically says exactly what it wants. Draw an example of a red-black tree, which is not an AVL tree. The reason why is because red-black is a lazier, I guess the way to say it, condition than AVL, right? And that's mainly because AVL maintains height difference of at most 1, right? Whereas red-black maintains height difference of at most, oh good God. Okay. Of at most n over 2. So what I mean by that is that if you have a height h on one side, you'll have height h over 2 on the other side, and that's just by rearranging red and, well basically, anyway, I'll let you think about that one. But yeah, red-black is a slightly lazier condition than AVL. Okay, so that's it for that. Okay, so let's get back to heaps. Okay. Oh no, I'm not heaps. Hash tables. I keep saying heaps because I'm thinking about the binomial heap or something. Okay, so remember what a hash table is, right? So let's get back to it. A hash table is an array, okay? I mean, you might say, but it's not really blah, blah, blah. It is, right? In secret, that's all a hash table is. But instead of using the indices straight up as value, as the way to access, we use keys. And then what we do is we store values. And so basically, normally we'll either use strings or ints as keys. And the reason why you use strings or ints and not usually doubles, it's legal but dangerous And of course, booleans are completely out, right? Yeah, I mean, so the actual answer is that if you're talking about a Python dictionary, that is exactly equal to a hash table. So I don't know exactly why Python decided to call it a dictionary. If you actually look at their implementation of their dictionary, they openly call it a hash table inside of the thing. They just decided to rename it and call it a dictionary. In some other programming languages like Java, they call it a hash map. In Ruby, they call it a hash. In C++, they call it whatever STL calls it, right? The point is that we generally call it a hash table. Well, of course I can, yeah. Yeah. So let's build an array. Let's see here. Okay. I think, let's see, 1, 2, 3, 4, 5, 6, 7, 8. Okay, good, 8. 8's a good number. So let's say that this is our array. And so remember that we have an array of size 8, and we have a hashing function, which in this case I'm going to make h of x equal to 3x plus 2 mod 8. Okay? And so that's going to decide, whatever our key value is, it's going to decide what our hashing hash values are. So let's do some examples where let's try to insert, let's say, and remember that this is going to be key value pair combinations. So let's insert something with a key of 5 and a value of, and I was always making the values, let's make the value happy, right? So let's insert this into the hash table. And so the answer is, what you're going to have to do is compute its position, right? And so to calculate its position, what you do is you do 3 times 5 plus 2, right, which is 15 plus 2, so that's 17 mod 8, which is 1 mod 8, right? So 5 and happy is going to go into slot 1. There we go. Have to shrink it down a little bit. Okay, so let's do another one. Let's do, let's say 22 robots, right? And so remember, the value is completely irrelevant. We don't use the value at all for hashing. We only use the key, okay? We only ever use the key. And so, okay, so let's calculate again. So 22 times 5, oh no, I'm sorry, 3 times 22 is 66 plus 2, which is 68 mod 8. I guess that's 4, right? So there we go. Let's put that into slot 0, 1, 2, 3, 4. So we'll put it into this slot here. All right, let's do another one. Let's say 17 and, I don't know, purple, right? So the value, again, the value does not matter. It's just, I'm just using it as an example, but because I think last semester I just wouldn't include values, and I think that might have confused some people. So anyway, okay, 3 times 17 is 51, and then we add 2, so 53. So what is that mod 8? So 53 mod 8 is, I think that's 5, right? It's 5 mod 8. Let's use the ye olde Windows calculator to verify. So 53 mod 8 is 5. So I was actually, A, I was actually right, but B, it's good that I doubt myself, because the problem is that if you make a mistake part of the way through the calculation, then it kind of messes everything else up. So this is basically how hashing works, right? So remember, from last time, we discussed the 3 methods of, and let's actually solve for a collision. So let's try to get a collision now. So I want something that maps to, say, 5 mod 8. So let's see, 5 plus 8t is equal to 3 times x plus 2. And so then if we solve it like this, we'll end up with what? Actually, we can subtract, so we can say 8t is equal to 3x minus 3. And then I guess we just do this until we get something that's divisible by 8. So, and then of course this is actually what, 3 times x minus 1. So let's just solve this a little bit. So, well, this is co-prime, so I think 27 maybe, right? Because 27 minus 1 is 26. Wait, what? No. But that's not divisible by 8. Let's try 25, because 25 minus 1 is divisible by 8. There we go. Okay. Times 3, so we got 72. Okay. All right. So I think if we try, I know that was all kind of a bit of an aside, but I'm calculating a value who will hash into the right place. I'm trying to conflict with, I'm trying to have a conflict with 17 purple, right? Okay, so here's what we do. So then what you'll end up doing is you'll say 3 times 75 plus 2 is equal to what? So 3 times 75 is 225, isn't that right? Yep, plus 2 is 227. Mod 8, I'm not brave enough to do that, is equal to 3. Wonderful. So somehow I made a mistake here. Interesting. Interesting. How did I make a mistake? So 25 minus 1 is equal... Oh, because x should have... Crap. X should have been 25. There we go. Okay. Okay. So 75 plus 2... Stop doing that. Okay. 75 plus 2 is equal to 77. Now let's mod that by 8. 77 mod 8 is 5. Okay. There we are. All right, so it's not 75 rhubarb, it's 25 rhubarb. Okay, so 25 conflicts with 17, right? It tries to hash into the same location, right? And so remember, we call this a hash collision, right? And so here's the problem with hash collisions, right? There's a question as to what you do, right? And so there's 3 methods, you know, as I said, about how to resolve this, right? When you try to put 2 things in the same spot, there is what we call linear probing, right? Where linear probing says what you do is you just insert it into the next slot, okay? So for instance, here what you're going to do is just stick it here. All right, so when you have a hash collision, you just start probing from the current place all the way around the array until you find an empty spot. Okay, when you do, you insert. All right, so that's the point here, right? So 17 purple was taken, but we put it here, and then when you try to resolve the collision, you just go to the next spot. So let's do something else, maybe something that conflicts with this. So actually, I think, yeah. So I want something else that mods in, mod 8 into 4 mod 8. But I think that's invariant when you divide by. I think that's okay. So let's try. What is 3 times So what is 20? So times 3 mod 8. Okay. Anyway, so okay. So that's one way to do it, right? And then the other way to do it was quadratic probing, where quadratic probing is basically when you have a hash collision, you jump to wherever the start position is, right, which is equal to the hash value of the key, right? So you'll do hash of value of key plus, it's not I, right, but it's I squared, right? So the first value you start at I equals 0, and if that one that's no collision. And then if there's a collision, you increment I until either there's no collision or you run out of options. Okay? So, all right, and let me show you some things about quadratic probing. So let's do a simple example. Let's not do this 3x plus 2. Let's just use the simplest hash function possible, right? Let's just use f of x equals x as our hash function. And the reason why we won't want to use the simple hash function is because then we can understand exactly what's going on. So let's do quadratic probing on the simple hash function. So let's say that our hash function is just key mod 8. And in this case, what we're going to do is let's insert, say, and let's insert 1a, right? Let's insert 4b, 7c, 14d, and maybe, I don't know, 20f, right? So if we do all of this, what we're going to end up with is we'll insert 1a here, and then we'll insert, let's see, 2, 3, 4, so we'll insert 4b here, and then we'll insert 7c here, and then 14 mod 8 is 6, so 14 is going to go into here, d. Let's shrink these down a little bit so that they actually fit inside their boxes. And then 20 is also 4. So let's look at that. So say 20f, right? 20f is going to conflict with this because 20 mod 8 is equal to 4. But remember, if we're using quadratic probing, then we start at the index 4, right? 20 mod 8 is equal to 4. So we start at the start index plus 0, right? That's taken. Then we go to 4 plus 1 squared, which is not taken. So we can stick things in there. So we can stick 20f into there. But now what happens if we try to stick something else that's also something mod 4? So let's try a new key, right? We want something that's also 4 mod 8, but hasn't been inserted yet. So let's come up with something like that. So what else is 4 mod 8? So I guess 84, right, is 4 mod 8. That's pretty easy. And so let's insert a key 84 t, right? So what are we going to do here, right? So we look at, in this case, what we're going to do is we're going to look at this place here. So we're going to say, okay, try to stick it into slot 4. The answer is we can't. And then we're going to try to stick it into slot 5 because 5 is equal to 4 plus 1 squared, right? So 4 plus 0 squared is taken. 4 plus 1 squared is taken. But now, what is 4 plus 2 squared, right? So 4 plus 2 squared is equal to 8, right? mod 8 is equal to 0, not taken. Okay, so let's do this. Here we are. So now let's come up with yet another one, right? And you notice that it's not going linearly, because here it skips over. So this is the first thing that quadratic probing looks at. Then it looks at here, and then it tries to go 4 more, so it tries to look here. And now what is it going to do the next time? So it's going to try to do, and then you're going to see a slight problem, right? Let's pick something else that's also 4 mod 8. So I guess 124, right, maybe? Or I guess 88 is 0 mod 8. So 92 and R, right? So that's going to be 0 mod 8 again. And so when we try to insert this, it's going to try to go into here, but it can't. So when we try, yeah, so let's write this out, 92R. So it tries to go into slot 4 plus 0 squared, taken. Tries to go into slot 4 plus 1 squared, taken. Tries to go into 4 plus 2 squared, right? Taken. And now it's going to try to go into the slot 4 plus 3 squared. But now you're going to have to think about this. 4 plus 3 squared, so 3 squared is equal to 9. 9 mod 8 is equal to 1. So as it turns out, this is just 5 again, right? So if you look at this thing, this is equal to 5. This is equal to 4. This is equal to, I guess, technically 0. But so that's a repeat, so it's taken. 4 plus 4 squared, so 4 squared is equal to 16, so that's 4, taken. 4 plus 5 squared equals, well, whatever 25 is. So 25 is 1 mod 8, so this is equal to 5 again, taken, right? 4 plus 6 squared, so 36 plus 4 is 40, that's equal to 0 again, taken. So, I mean, I've gone on way too long, but you kind of see the problem here, right? There's still empty spaces, but you see that quadratic probing is never going to find certain spaces, okay? And the reason why it's never going to find certain spaces is because, as it turns out, when you pick a number, m, there are only a certain number of squares. And the answer is that the number, I should say, squares mod m. And so, for instance, if you look at like the mod 10 system, the squares are going to be 0, 1, 4. The next one is 9. And then we have 16, so mod 10 is 6, right? And then 25 mod 10 is 5. But then 36 mod 10 is 6 again. 7 squared is 49, so 9 again. 8 squared is 64, so 4 again. 9 squared is 81, so 1 again. And then 100 squared is 0 again. And then as it turns out, it just repeats. And so you'll see that you're never going to see the numbers, 2, 3, I guess, so 4, 5, 6, and 7, 8, right? So basically what we say about these numbers are that these are all the quadratic residues mod 10, and these are, I guess, quadratic non-residues mod 10. And so you see that there's just numbers that are just never going to occur. So it's always possible that a non-full quadratic probing hash table will not be full, and yet still not be able to insert any particular element. And the reason is because here what I've done is I keep colliding with 4, right? I keep doing this hash collision with the key of 4. And so the problem is here that you see that quadratic probing is never going to be able to hit the offsets of 2, 3, 7, and 8 mod 10. Or for instance here, actually it's even worse, because mod 8, it's never going to even be able to hit, basically the only quadratic residues mod 8 seem to be, what? So 0, 1, and then 2 squared is 4, 3 squared is 9, and then 4 squared is 0, 5 squared is 1 again, 6 squared is 36, which is 4 again, 7 squared, which is the last one that we really have to consider, is 49, and 48, so it's 1 again. And then 8 squared is 0, and so this repeats. So we see that the numbers 0, 1, and 4 are quadratic residues. And basically, 2, 3, 5, 6, and 7 are non-residues. So basically, quadratic probing on this value is going to produce almost no good values with a hash table of size 8. With a hash table of size 10, at least it produces about half of them are quadratic residues and the other half aren't. I guess actually 6 out of 10 and 4 out of 10, so it's something like that. But the point is that that's how quadratic probing works. All right. And so remember, if you were doing linear probing, right, if we were just doing linear probing and this conflicted with this, then all we would have to do is just go, doesn't fit, doesn't fit, doesn't fit. Then you loop back here, doesn't fit, and then here it fits. Right? So you keep looping around until you find a place for it. But of course, that's not the case when you do quadratic probing. So when you do quadratic probing, you cannot just go one by one. The indices have to be squared, or I should say the offset from the index has to be squared. Okay. So and then the last thing to say is that this is not the only solution, right? The other solution for this kind of thing is chaining, right? So sometimes you don't want to do linear or quadratic probing. So without linear or quadratic probing, you can still chain. And so let me explain what chaining is. Chaining is if you have a data structure, so you need an auxiliary data structure, maybe a linked list or tree or something. And what's going to happen is that if there's ever a hash collision, you resolve it by just inserting it at that position under the into that data structure. So for instance, here are the ones that collide, right? And then the 92, I guess, also collides. And so the right answer here, when you're doing chaining, is going to be that there's going to be a linked list that appears, right, here. And so that's going to be the way to resolve these collisions. Now, so doing it with a linked list is not great, but, you know, who cares, I guess. The right answer is like, and so let's look at all the advantages and disadvantages of all the different methods. So remember what the advantage, you know. And so here's our assumption. One assumption that we make is that the hash O of hash is O of 1. Okay? So, and the reason why we assume this is we're going to assume that it takes constant time. It's not necessarily 0 time. It does take time to hash a key, but it doesn't take time. I guess what I'll say is this. The time it takes to hash a key doesn't depend on the hash table size or on the number of elements inserted, okay? So if it only takes O of 1 to hash a key, then as it turns out, insertion, right, is O of 1 in general, okay? And so that's the point, is that in general it's O of 1, which is great. But if we start getting a lot of hash collisions, then the problem is that the table is going to fill up, right? And if the table fills up with a lot of collisions like this, then the problem is that you aren't going to know how far you have to probe. So for instance, if I was looking at, let's say I was looking at this table here, and let's say that this was linearly probed. So instead of being quadratic, let's say that this is linear. So the point is, like, if I ask to search for 92, I'm going to say, okay, let's search for 92. And then so what we're going to do is we're going to say, okay, I know 92 is 4 mod 8, so I look in the slot 4. It's not there, so I have to look in the net. So just because whenever you do linear probing, that means that your find also has to do linear probing, because you will have to be able to find any of the elements that you insert. So insert and find have to do the same kind of probing, right? So here, if you have 4b, well, I know that the thing I'm looking for, let's say I'm looking for 92, it isn't that, so I'm like, okay, keep going. Here I get to 20. 20 also is 4 mod 8, but it's not the right key. So keep going. And now here's the real kind of tricky part, right? Let's actually write this down. So let's say that I'm looking for 92. Right, I start at 4. Nope. And so then I have to start probing. So I go to 20. Nope, it's not 92. Keep probing. And then I get to 14, and I say, nope, not 92. And then, so here's what somebody might say. Objection, right? 14 is actually not 4 mod 8. It's 6 mod 8. So it's not the right value, so can we stop? And the answer, unfortunately, is, the answer to this is no. You can't stop, and the reason is because I don't care if you linearly probed or you quadratically probed, you can't stop here because you see that there's some other things here, like 84 and 92, that got stuck in after that element. So the problem is you can't stop probing here, so you have to, even if you find a value whose hash is not equal, you still can't stop probing, okay? So let's keep probing. So 7, nope. 84, nope. 1, nope. 92, yep. Okay. So that's how you would find it. So now if you look at this and you say, what's the time complexity of this, right? Right, and the answer is that if there's a lot of kind of bad probing going on in terms of insertions and finds, the answer is actually it's O of n in worst case. Right, where n is equal to either size of hash table or number of elements inserted into table. And the reason why we don't really care which one it is just because as n gets close to the size of the hash table, right? As n gets close to the size of the hash table, right? O of s is equal to O of n, so we don't really care. But you see the problem here, right? The problem is that this is going to cause us an issue because our goal was to have an O of 1 data structure, right, for insert and find. But here we have an O of n data structure for insert and find. So as it turns out, the worst case for hash tables, right, is worst case for hash tables is really, really, really bad. And so the question is, how do we fix this, right? And so the general solution, at least that, I don't know if it's the best solution, I don't know if it's the, I don't have a mathematical proof that it's the optimal solution, but generally what people do in this case, right, the solution is you double the size of the underlying array, and then you rehash everything, okay? And that could be, so this is an expensive operation, right? So, but let's do that with this, right? So if we're going to double the size of the underlying array, then we will do something like this. And then let's delete all the inner stuff. There we go. Now let's take all this inner stuff and move it out, since we're going to have to rehash everything. But now, right, so now our hash function, right, your hash function gets modified, but it's not really modified in terms of h of x equals x. The only difference is that it's mod 16 now, rather than 8. Okay? But you'll see what difference this makes. Let's try to reinsert all this stuff. So first, 1a is going to go into here, so that's pretty easy. And then let's put 4b, so this is 2, 3, 4, so we'll put 4b into here. And now let's insert, I don't know, 7c, so 7c is the, 3, 5, 6, 7, so we'll put it there. Okay. So 14d, remember last time it hashed to 6 because it was 6 mod 8, but this time it actually hashes to 14 because 14 is just 14 mod 16, right? So you see what's happening here. It's spacing everything out. And so here, and let's do this with linear probing. And it's going to start to matter in just a second. So what we see here is that with linear probing, 20 mod 16 is equal to 4. So even with that, we're still having a hash collision. So, but that's fine, right? Because here we're going to just do this, right? Linear probe, and just stick it in the next slot. Right? It wanted to go in here, but it couldn't, so we're just going to stick it in there. And so now the question is, what is 84 mod 16? I think, unfortunately, isn't 84 mod 16 going to be 4? Yes. And then what is 92 mod 16? I think that will be, is that going to be 12? Yes. Okay, so unfortunately, this one is also going to try to insert here. It can't. It's going to try to insert here because it's going to do linear probing. It can't. So it's going to get stuck in here, so that's good. But then you see that here, this one is going to get inserted into slot 12. So 7, 8, 9, 10, 11, 12, and that was the stupidest thing I could have done because 14 was here. I should have just counted back 2. But anyway, so that's, but you see, what's the point of doing this, right? The point of doing this is that now the load factor is far lower in the hash table, where, remember what the load factor is, often denoted lambda, like a capital lambda, is equal to the number of elements divided by the number of, let's say, the size of the array, right? So the number of elements is 1, 2, 3, 4, 5, 6, 7, and the size of the array here is 16. So a hash table, it usually expects that the load factor is under 1/2. And the reason why that is if you think about it, what is the probability of a collision, right? Assuming that all keys have equal value, right? Assuming all keys have equal value, the probability of a collision is lambda, right? The load factor, right? And so that's the whole point of the load factor. The load factor is actually the probability of a collision, given that all, I shouldn't say all keys have equal value, I should equal probability, right? So, and so if you have a collision, that's what's going to cause you to start to have, you know, bad stuff start to happen, right? And so basically here, you can calculate your expected time complexity, right? Your time complexity is going to be something like it's going to be 1 plus the probability of a collision, plus, say, the probability of a collision squared times 2, plus the probability of a collision cubed times 3, plus some power series like this. And the reason why it's going to be like this is because the cost And now we're assuming that collisions are independent. So if collisions aren't independent, or the load factor is too high, and this number is too close to 1, like for instance, then we're going to end up with a major problem. So, but yeah, basically this is the expected cost of an insert or find. And so the point here is that if you have 2 collisions, that meant you have to search twice. If you had 3 collisions, that meant you had to search 3 times. If you have 4 collisions, that meant you have to search 4 times. And it is true that I'm assuming that the probability of a collision is independent, meaning that the probability of getting the first collision is the same thing as the probability of getting the second collision, which is the probability of getting the third collision, which is definitely not always true. Especially in cases where I just continue to attack the hash table with this particular, not key, but hashed key, right? Where I'm just trying to hash everything into 4. So there's even a term for that, and I've already said it, but the term is actually called a hash attack, and it's where you try to reverse engineer the h of x function, and then insert. Basically, you insert using the key, which is just the hashed key, which is basically only going to go 1 or a few positions. So basically, mostly what you're going to do is you're going to insert stuff that only goes into a few positions, so that most of the hash table is empty, but then the full part of the hash table, or I shouldn't say the full part of the hash table, really most of the hash table would be empty if we use like chaining. If we chain, or really we're filling up the hash table with a bunch of data that all has the same hash. And so the problem with that is that the hash attack is going to cause an O of n, right? So that's the problem with hash tables, is that if you're not careful, you can cause a hash attack where people can just insert things with the same value until eventually they kind of overwhelm your hash table and cause O of n performance rather than O of 1 performance. And you know the difference between O of n and O of 1, especially if you have something like, pretend n is equal to, 100 million elements or something. It's going to be a significant problem, right? And so the thing that most people do, so I mean for teaching purposes, right, h of x equals x is great, right? But most hash functions are, or should be designed to prevent simple hash attacks. And so one example is basically you can use like a power series, like if you pick a polynomial. Say if we pick a polynomial like, a plus bx plus cx squared plus dx cubed plus ex to the 4th or something, right? So this is just some polynomial. What you can always do is you can say, okay, the hashed value of x is just equal to that polynomial of x mod the size of the table. And so the one thing you can't really control is this mod size of the table. You always need this mod size of the table. But the hashed value here is, if you use like some polynomial, then the thing is that the nice thing about the polynomial is that sometimes what you're going to end up seeing is that different values, like if you insert a whole bunch of things that look like they're the same, hash collisions, right, require solving, right, p of x equals, right, say the same thing, right, the key value, mod size. And so the answer in general is that if you tried to solve this, there's only, what, like 4 solutions since it's a quartic. Of course, there's going to be multiple solutions, more than that, because it's because we're using the mod system. But in general, it's kind of hard to solve the problem. And so it's a good hash function, since, you know, most hash attackers are not actually going to solve like a quintic equation, right? Or a quartic equation won't solve a quartic, right? So it's a decent method to try to avoid it. Of course, you have to be slightly careful here because it's always possible that if you pick a bad polynomial that you'll end up missing values, just like with quadratic reciprocity. But it's better to pick some kind of thing like this. And so that leads us into an example of, so here's an example for strings, right? So for strings, a good hash function for strings, I'm not saying it's a perfect hash function or anything, is that you would say, like, if our string is just called C, then you could do C of 0 plus C of 1 times, I don't know, X plus C of 2 times X squared plus C of 3 times X cubed plus C of 4 times, you know, X to the 4th plus dot dot dot. And then the last one, Cn minus 1 times X to the n minus 1. And then finally, you mod it by n. And so that's a hash function for strings. You can also just, the simpler hash function for strings is just literally just add up their ASCII values. So you sum up the ASCII values of the characters, and then you mod it by the size, right? So this is a kind of more general one where you attach a little x to each one. And this kind of mimics the polynomial functionality of this kind of thing. So yeah, I had intended to, I guess, live code a hash table during this lecture, but I guess I just went over all of hashing again. So this lecture is mostly identical to the previous lecture, I guess. This stuff is new, about talking about hash attacks and hash not hash collisions themselves, but talking about hash attacks and coming up with better hash functions. But you see the problem with using any of these, so they're really bad for teaching, and the reason why is because it's really hard to guess 2 values which are going to hash the same hashed key, right? But they're great for real life for exactly that reason, right? So it's very difficult if I just told you that, like, oh yeah, I'm going to use some polynomial like this to hash or something, you're going to have a very hard time discovering what all these coefficients are or all this stuff, and you have to solve this. It's hard. It's actually kind of difficult, right? It's really an algebra problem. And it's a very hard algebra problem. And so that's a good bit of news. So the good bit of news is that, like, if you can make your problem sufficiently hard, right? Or really what I mean by this is, I guess, what I mean by this. H of x is a function. We want it to be a one-way function, which is something you hear in cryptography. What I mean by a one-way function is it's a function where h of x is easy to compute, understand, whatever, right? Like, I don't care that it might be hard to solve for roots of this polynomial. The whole point is that it's easy to understand what the polynomial is, right? You know, if I ask you to compute any value, if I say x is equal to 5, you can compute what the polynomial is. If I say x equals 7, you can write a computer program to compute whatever the polynomial is. So you can definitely compute whatever values the probability for the polynomial is. So that's easy in the first direction, right? Easy to understand, compute, deal with in general, right? But h of x, or I should say h inverse, right? So the inverse function is very, very hard or impossible to compute or understand, etc. And so this is the idea of a one-way function. A one-way function is a function where in one direction it's easy, but its inverse is actually very hard to compute. And polynomials, I don't know that you would say that polynomials are necessarily examples of one-way functions, but I think in terms of hash tables, they definitely can be. And the reason is because it's easy to understand how to calculate, given a polynomial, what the answer is that comes out of it. But then if I ask you, like, oh, just solve, right? I mean, the problem is, like, even if I gave you a cubic, right? 5x squared minus 2 equals 0, and I just told you, solve this equation for me, right? I think most people are going to, I think most students will object. And the reason why you're going to object is you're going to say something like, hey, wait, I don't really know how to solve cubics. Or you'll forget that you don't know how to solve cubics, and you'll say, can I use the quadratic equation? And I say, no. And then you say, okay, can I use the cubic equation? And I say, sure. But the cubic equation is much, much more difficult to understand than the cubic itself. For instance, let's see. Where is it? So yeah, here's the cubic. Here's part of the cubic equation. This is what the cubic equation is, right? And so that's not terrible. But then I say, okay, well, if that's too easy, right? So you think the cubic equation is too easy. We can solve that. So then I'm like, okay, just increase the degree, right? All right, now it's a 17th degree equation. And so A, there's no 17th degree equation for solving for the roots. So that's one problem. And B, even if there was, it would be really, really, really hard to understand. So that's kind of what we mean by a one-way function. So as it turns out, polynomials are a pretty good thing. There's a bunch of other, you can come up with other things, but I think most things polynomials are probably the best kind of compromise because they're easy to compute, so you keep the O of 1 hashing time, but you can make really complicated, totally hashed up keys or key values with that. And so remember that the whole idea, the whole reason why it's called a hash table, right? Like the origin of the term is exactly that. And what I mean is that, I don't know if you've ever heard the expression, make a hash of it. Basically scramble it up. Make it unrecognizable. Right? Take a potato and make it into a hash brown. Right? A potato into hash brown. And so that's the idea, right? And so basically, it is, there's nothing complicated about the word hash. It literally just means, take whatever you're doing and just scramble it up. And so, as I say, for teaching purposes, you're basically hardly ever going to see me use a very complicated hashing function. Generally, I think, h of x equals x is a pretty good hashing function. You see, even with like 3x plus 2 mod 8, and that's a slightly harder hashing function, but that's generally easy to solve. But this one, if this were our hashing function, this would be extraordinarily hard to solve, right? And so that would be an example of a good hashing function. So, all right. I think that's really all I have to say about hash tables. Basically, the expected case of insert find is going to be O of 1, but the worst case Yeah, I can change it to allow resubmissions. Yeah, I'll do that. Okay, the worst case is going to be O of n, right? And so this is what we're trying to avoid at, well, I won't say all costs, and all costs, I guess, even though it's not really all costs. We're just trying to avoid it as best we can, right? It is definitely possible that we end up in an O of n case through either hash attacks or just bad insertion of values or picking values that all have the same hashed key, all that stuff. It's totally possible, but, you know. Anyway, okay. So I think with that, we are done for the day. So I'll let everybody go, and then I'll change that thing. Okay, what am I doing? I am running the outro. Goodbye, everyone. Changing the number of attempts. Okay, that's done. All right, so that should be done. All right, everybody. See you later.